Hi. So I've got a lot of material to get through, so I'm going to start us right off. My name's Kate Stewart. I work at the Linux Foundation, and my main focus there is how do we make embedded systems be dependable. And so functional safety is a large part of that, as is security, reliability, maintainability. And so, one of my first memories, literally, of something that was happening in the world outside my family was being called by my dad to watch the moon landing, okay? And that moon landing would not have happened effectively and efficiently without all the testing that this woman did, and her team actually, to actually make sure that we actually got people to the moon and we actually were able to recover from failures. The key for safety, as opposed to regular development, is being able to recover from failures when things happen. And she gave a really good talk at ICSI a couple of years ago before COVID, and it pretty much defined the start of the safety culture that we started coming into standards today. But realistically, building man-rated software, the astronauts' lives were at stake. It had to work the first time. And you have to detect errors and recover from them in real time. And in some ways, this is still at the heart of what safety is all about. And, you know, everyone was moving fast, didn't know what they were, basically coming in, trying things, trying to make it happen, trying to make it probable. You know, the managers at the point in time were hardware people, and they were working with software people. Software was still in its infancy at this stage compared to where we are now. So everyday systems today have safety functions in them that we encounter, from your cars to trains to planes. All of us getting here have probably been on a system that has safety associated with it, and quite frankly has software running underneath it. Home automation has it, medical devices have it. You know, it is around us, and we are taking it for granted for a large part of the time. And there's lots of new functionality and cool stuff emerging that people want to bring these functions into safety. And so figuring out how we're going to be doing that, where the innovations coming in from open source is sort of at the heart of this. And the other whole area is all the critical infrastructure we depend on as a society is running on software today. So safety itself can be sort of thought of as a spectrum. And this is also important to understand, in the sense that, where's my mouse? There's my mouse. It goes from very light things like something that's quality managed. So things like going after MISRA compliance, being consistent, having configurations, and that type of thing is sort of the starting point of this. And then there's different levels of integrity and testing associated with it for recovering from the faults and showing that you have been able to recover from the faults. So literally there is this full spectrum that sort of goes up to the higher levels. And, certainly the fact that, the aerospace and so forth are, making sure that, these highest levels are achieved and things are going to space because of the costs and so forth in people's lives. So very much visible. So what's been evolved as a methodology in the safety space is something they call the V model. And it comes from the notion of requirements. And the requirements are coming from the stakeholders. So you're looking at a system. You're not looking at a component or a project. You're looking at what the system has to do, and then figuring out which components can go and make that system happen, and what are the requirements successively down. And then you come up with testing to prove that you're satisfying those requirements. Now, the satisfaction links will basically show that you've actually done it, so to speak. And so safety is assessed for a system. And the same way you'd end up starting to build a bridge or build an arc, you basically, you've got all of these components and you're basically putting them together in a way that's going to be structurally sound. And so this image, just for reference, is from an awesome simulation of how they built the Charles Bridge here in town. And I would encourage anyone to check that out. You'll be seeing more pictures from there later today. But it's showing how as you build an arch, there are keystones. You've got all your stones shaped, and it's together, it's solid. And what we're trying to do is effectively take the blocks of open source we're working with and figuring out how we can put a framework to build them together so that they'll be solid when we want to use it for safety. Today, historically, most of this has been done behind closed doors and under NDAs, mostly because it's been liability and risk and liability aspects are controlling because people's lives are in danger, and if something goes wrong, someone's going to come and sue you. Automobile recalls, things like that. are things we see commonly in the news. Obviously, a very sad example that just hit, we've been seeing on the news, is the decompression of that sub that was looking at the Titanic recently. They were very visible about the fact that all this safety stuff was just slowing down their innovation. Well, 5 people have died now because they didn't do some of the analysis that they probably should have done before they put people's lives at stake. Open source is a large part of what we're seeing here in this innovation. Most of the code bases right now are open source, and a lot of open source is being used in safety. It's just not very visible. And there's ways we can mitigate it because we're taking up things as a system. But trying to get these components accessible, more accessible is part of what we want to do. And back to the Apollo 11 example, all the code there is now open source. So if you're ever curious to see it, you can go out and look at it. And actually, Software Heritage has also logged it as part of our history. But open source, it speeds innovation. And so it makes it possible for us to build things because we're building on things that other people have done. And so modularity and building things together is a real part of this. So the open source ecosystem is usually composed of things that I consider like projects, like Zen, obviously, Linux kernel, things like that. Build systems that assemble these things into executable images, test frameworks to check if these requirements are satisfied, make sure that it's functionally correct. And then there's metadata to understand what's happening. We see all this out there today. And then there's distribution sites, GitLab, GitHub, et cetera, where you can pull these components from and put them together. All of these have a role in some of the ecosystem. And very active. And so it also plays into where we might have a bit of a software development culture clash that's been going on. Pretty much the open source software is project-based, uses agile, DevOps flows, and so forth, whereas the functional safety development starts with requirements, decomposes it, and has a more structured approach to putting these pieces together. Why is there a culture class? Well, it's not, open source isn't a problem, but it is difficult to map what they've been used to looking at as evidence to what actually is coming out of open source. And, the Agile Manifesto says fail fast. Well, if you set something to fail fast, someone might die. So there's a balance here of risk, and how do we actually make it so that we can, working with open source, make it possible to be used, and the right evidence and analysis happen, okay? And so we can go in this, like I say, that is sort of at the heart of where this culture clash is coming at, Users need the accountability. We want these rich features, we want these new things to do, exciting things that happen, explore things, but who's liable if something goes wrong? And no one wants to be first on this whole thing. However, failure can result in serious harm and death, which is why there's a safety story happening. So, are we actually compatible with software standards? Yeah, short answer is yes. But we have to basically look at some transformations. And, people are doing things right now with open source today that are safety critical, okay? I know this from talking to a lot of product makers, but none of this is in public. And, they fork initially, they do things, maintain them, they hold things stable long beyond their lifetime in some ways, that makes things vulnerable potentially for security. It's expensive. It's also a problem that the standards themselves that we want to look at for various domains have knowledge for those domains. They're behind paywalls of about $5,000 each. As a hobbyist, or even as a company that isn't doing safety as a regular spot, but I'm a maintainer, I'm not going to go spend $5,000 of my own money to see a document, unless it's directly related to my, what I'm doing for my job or my boss is paying for it. And so, and there's also many standards out there. There's a whole network of them that interrelate. So you get one, you start looking at it, and then it goes through to another one, and another one. And if you're actually in the space, you've made the investment in it, and you have access to it. But if you're not in the space, and a lot of the open source contributors are not, you don't see this stuff. So how are we going to approach safety assessment with the open source software components? Well, taking a little bit of a inspiration from the bridge here. What we need to be looking at is, we need to figure out how we're doing these blocks, and then the process for putting these blocks together in a structured way to actually build these components in a way we can figure out. When you're starting to look at building a bridge, your first thing is, okay, what type of bridge is it? Is it a bridge for cars, a bridge for people, a bridge for trains? What are you going to be running on that bridge? That's a requirement at the heart of it. And so that starts the first set of figuring out how this system might be composed or how this bridge might be composed. For our bridge here, it's, we need to figure out, define the scope and limit, and figure out methodology for better describing a system. Zen is going to be at the heart of a lot of these systems. We need to start figuring out how we document requirements in a way that are discoverable and testable and can be proven in use. And then how they understand how these components are going to be used in the system a bit better. And then automate as much of this information as we can. Right now, the processes that I'm seeing are proprietary tools and a lot of manual spreadsheets. I talk to safety assessors, that's what they're using, and that's what they're seeing still. Anything that's done that way is, I would consider not optimal for what we need to do for the pace of software change. We want to be able to auto-generate these documents from the test and the issue tracking systems. This is evidence. This lets you know that, yes, you've done the right level of testing. And so this stuff needs to just come out automatically. And then we have to get, if you're going after a safety system, engage the safety assessing people very early at the system level to say, are we thinking about the right blocks together? These are processes, and then the question is, so how are we going to harden things? Well, open source already has a lot of strengths, okay? Code is available publicly, and it can be scrutinized by anyone. So that transparency is a tremendous advantage. This is the reason Linux kernel has been so popular over the years, to a large extent, is because people can go look at it and say, hold it, oh, okay. Code reviews are happening publicly. People aren't letting things into their maintainers are basically very much responsible for not letting things in until, hey, it makes sense, it's coherent, okay, fine. And then the test infrastructure is open as well, and it can be extended. So you can have something partially there, and you can do a lot more behind the scenes if you need to, but hopefully more and more of the testing will eventually be upstream too. So, there are limitations, though, in terms of, do you have the right experts looking at things, which is something the safety standards look for? Who has the final say? And, how do we guarantee that reviewers are aware of the safety implications? And, how long should be the change review? So there's some process issues still to do, but we have a lot of things we can build on here in open source already. The challenge was, as I'm saying, we don't have any good examples of how to do this publicly. So we're busy coming up with this in different ways, in different projects right now. And we're experimenting a lot. There's a lot of innovation happening, a lot of let's try things, let's try and move things forward. How can we get this happening publicly? And there are different criterias on different standards. And so what are the common underlying pieces? And how do we focus on that? And each expertise area does have different concerns. Again, those are those standards behind the $5,000 per pop paywall. But if you're in that area, you might spend it, but otherwise you might want to make sure that the open source side at least is adhering to enough general principles that you don't need to, that the developers don't need to, as the maintainers don't need to. So writing these open source building blocks, I'm going to talk a little bit about those blocks that you'll be assembling into the bridge. These projects like Zephyr, Zen, and ELISA, which is for Linux, effectively. And it's looking at, okay, how are we looking at trying to make the evidence visible and available so that we can hook this all together? And then the other side of it is, okay, how do we start having a process framework so we get this all automated and get the automation of the metadata as well as the build infrastructures happening in a way that's useful for these going after safety use cases. There's other ones out there. These are the ones I know best. And so if people want to talk to me about other projects I should be considering in my overall ecosystem of safety friendly or safety aiming at ones, I'd be welcome. So quick show of hands, how many know Zephyr? About half, okay. Just quickly, Zephyr is an open source real-time operating system. It was designed to go where Linux is too big. So think 10K and up, okay? As opposed to Linux doesn't, 3 meg is the smallest as Linux gets right now. And so when you're on sensors and actuators, you still need that element because there's safety elements associated with making sure things work. It is, it basically was started with safety and security in mind, the project. We knew we wanted to go after safety eventually with it. We focused initially on security, getting it so we had all best practices applied, and then we've been moving up from there. It's supported on a wide range of architectures already, and we also have over 120 sensors already integrated, and there's over 450 boards in the repo. I think over 400 of which are for ARM processors, just for a side note on this. But we've got a rather wide ecosystem here with Zephyr and a lot of options available to start. And so people are starting to look at it for things that we'll be using for safety. And there's a rather complete stack already. And we've taken the lessons from the kernel in the sense that we have community contributions to the DCO, active development. There's releases that come out every 4 months or so, and then every 2 years we do a long-term support. And it's a subset of this long-term support. We're doing the initial analysis and documentation to take it to have a subset of the requirements be auditable. So we've been doing this now for 2 cycles for LTSs. We're coming up on our 3rd one next year. We've basically been doing our best to follow security best practices. We actually can automatically generate out SBOMs as part of the project as well. And we are using the various scanning technologies out there. And the initial safety focus for it will be just the kernel portions. And we are going to be going after 61508 SIL 3 with the Root 3S. So when we're looking at x86 and ARM as our initial focus, and then the idea is, as we show people how to express requirements, tie it to the code, tie it to the tests, and do that publicly, as people want to start adding more features in, hopefully they'll start adding the requirements, so things will build over time. So the question here is, how do we get ourselves at a state where we can catch this information and then basically prove it? And quite frankly, that's going to give better code for everyone. There's some collateral. There is generally used as part of a safety assessment, and some of it's going to be public, some of it's not. We're still reassessing this, so this side will change. Probably in the next couple months, you will see a different version of this. But we are trying to follow that requirements-based V model with this project so that we actually have the features specified, the documentation linked, the traceability, and providing the evidence. Now, the Zen project, I'm going to say, tune in tomorrow and get Stefano's and Bertrand's talk on this, because they will be going to a lot more detail that I'm going to have time for, and they are working on their slides now. Or they've got their slides done, but I won't take all their thunder. But anyhow, at the heart of it, they're aligning to MISRA coding standards like Zephyr is. They're starting to do some reverse engineering like Zephyr is on the documenting the requirements. And then AMD is working on explicitly a safety certifiable target for both AMD, ARM and AMD for ISO 26262 and 61508 SIL 3 like Zephyr is. So these 2 projects are both sort of aiming at roughly the same sort of targeting area. Now, ELISA is Linux. And how do we work with Linux in safety applications? It's already there today. Tesla cars, SpaceX rockets are nice public visible versions of it. But it's, in a lot of medical devices, it's in a lot of places that you would, like I say, they're using it, but they're mitigating it and doing the assessment. Anyhow, what it comes down to, assessing whether a system safe require understanding that system, selecting the Linux components and features that can be evaluated for safety, and then, understand how it's used and identify gaps, and then putting arguments in place to work around the gaps. One medical device that's out there that's actually public is the Open APS system. They're using Linux on a Raspberry Pi to connect a glucose monitor and an insulin pump. So while Linux itself is not providing the algorithm, that's happening in Python somewhere, it's being connected and it's requiring the reliable connection to the hardware. And that part forms a loop that delivers insulin to people. And it's improved the quality of people's lives. So we see Linux in spaces that are not, hard, real-time, very deep, but nonetheless have a function, and we have to assess the safety implications of that. And, the kernel's got a huge ecosystem, lots of capacity, multi-core support, unmatched hardware support, and experts. And the hard real-time stuff is actually making its upstream now, and it's still missing some of those aspects, as well as the proven safety compliant development processes. And so, this is part of the gaps. So ELISA's looking at, okay, how do we come up with processes to make this stuff more determinable? and trying to make sure that whatever we do is accepted by the open source community and ultimately upstreamed into the kernel. So the limits on ELISA project is we're not trying to create a safe Linux, okay? It's a myth that seems to be out there. What we're trying to do is help people figure out processes to take Linux through safety certification and figure out the mitigations. And, and basically try to build up some industry norms, have people to collaborate with and try to figure out, okay, what's working, what's not in this space. From a strategy perspective, what ELISA is doing from a deliverable side is a lot of working groups doing analysis and then sharing the analysis publicly. That is the key here. And make it available for information for system integrators to use Linux. And so how this turns into is, we've got an automotive use case group looking at 26.26.2, and they're looking at the Telltale use case. Medical devices working group has been looking at the Open APS system because we could do the analysis. It was public. It was an open source project. And so everything was there for us to do the analysis and start it from. And same with Telltale. And then we've just started an Aerospace working group. So Boeing joined us and is starting to look at how do they start to consider Linux in the aerospace industry. And we have a group focusing on the processes. How do we actually do this? We have a group focusing on the internals of the architecture of the Linux kernel, and what are the safety implications of things like the scheduler, or memory management. These types of things where if something goes wrong, it's going to affect everyone. And then, the Linux features, like real-time Linux. How can that be deployed and used effectively? All of these are going together in a systems group, and then we have basically a tooling group to put a reference system together and to have it stable. So it's an experiment place. So ELISA is a place for experimenting, and hopefully we'll figure out some steps forward. In particular, there's a systems working group where Zen is the hypervisor we're using, and assembling all these pieces together in a reference system that anyone can go look at and see how it's configured, and then be able to use it and build and evolve from that. So, and this is mapping with systems that safety is caring about at the heart of it. So we had a workshop last week up in Berlin, and we've basically been talking about how we can be pragmatic about some of this. Everything's pretty much got to get upstream to the kernel or the docs. We need to be making the evidence more discoverable. There are things out there that people just don't know about that help on the safety and argumentation. And we have to make things more provable from a requirements perspective. We had a fair amount of talking about the APIs and, those effectively document requirements. The man pages are effectively documenting requirements. How do we reverse engineer that and then show that things are coherent? So we've actually now had, in the last year, we've got a section up in the Linux kernel in the users and integrators section of the documentation that got upstreamed. And so one of the pieces of output, so we've been doing from one of the groups is, discovering the kernel subsystems by running the workloads, effectively a tracing, and how some methodologies of using some existing tools can be used to basically to cover what the critical paths are when various workloads are executed, so that we can start to do the analysis of the parts of the kernel that might be contributing to a safety argument. And so if you're interested in learning more, there's a white paper there. Feel free to sort of read it, and then people are welcome to join in. Another project is Yocto, and Yocto is basically been focusing on improving the dependability for a while through the reproducible builds, and having everything to be fully reproducible, which is something we're going to need on the safety argumentation side. And they've also got the automatic SBOM incorporation for transparency. And the reason I'm sort of focusing on the SBOM side of it is that's where the metadata is we'll be able to leverage eventually. So building images from source code, we've got the BitBake infrastructure there today. That's there. And we can work with a variety of images in Yocto. These slides, by the way, are from Joshua Watt. And he's got some really good videos up on YouTube that go into this in much more detail. Anyhow, the host tools will basically use the SHA-256 for, again, managing the reproducibility and actually integrity of the efforts and making sure nothing's changed out from under you, which is something we're going to need there. And we can also auto-gen with a change in the config file all these SPDX meta documents for the build tool chain, which is something that the safety that you need for safety. You have to demonstrate your build flow as well as the tools to do your building as well as the actually sources are function in safety usually. And the relationships that are there explain how these things fit together. So you can start to have a knowledge graph of what's going on underneath your software that you can figure this evidence from and figure out what you might need to test. And most of the stuff that Yocto is generating are things that are going to be needed for the safety cases as well as security. And so as you can see, we've got most of it happening right now, and rest and go are works in progress. Now, SPDX, you've been hearing me talk about SBOMs, so I'm slipping in a little bit of this stuff. Anyone who wants to know more, feel free to propose a session. I'm happy to go into more details. SPDX is an open source standard, and we went through ISO formally, and it is an open standard that does not cost. You can download it for free, okay? And you can also, it's also a living standard, and it's evolving. Specifically, it's evolving for safety. Critical infrastructure, the Japanese government last year published out for cybersecurity, published out here's where we need to improve. And the number 2 point was maintenance of the safety profiles, okay? Safety is important here too. As you can tell from critical infrastructure, you don't want something to stop working there. Now, those safety principles are looking for things that are things like unique IDs, dependencies of components, build configuration, existing bugs and their workarounds. All of this is stuff in SBOMs today. Over here, all these standards are looking for things like documentation, requirements for the software components. This is what's missing today. But we're fairly close. And so the challenge is if you have a security fix you have to apply, how do you know you're done after you've done it? Well, you have to basically make sure your requirements are adhered to again. And what the SBOMs do allow is the promotion of the requirement stuff. So you can actually test to your requirements. An SBOM at its heart, the definition people are working with right now is it's just basically components. And a component could be a file, or it could be a package, or it could be a group of packages. A distro, for instance. These are all components, and then they have relationships between them. It's just defining a minimum dependency relationship right now, but as you see, we can use a much richer set of relationships to connect the information with some degree of knowledge. And when should you create it? Well, all the key information you need for understanding what's really going on is happening throughout the software lifecycle, okay? And so you want to generate your SBOMs based on the information that is accurate and you know as fact, as opposed to guesswork and heuristics by scanners. So the OpenSSF and then the DHS CISA group basically spent a fair amount of time trying to deconflict the term SBOM by saying there's different types that are out there right now. There's things that happen to design, source, build, when it gets deployed, putting the configuration information, what's happening at runtime. These are all very useful things with different parts of information. And as you can see, they logically fit into different parts of our life cycle. So you can come up with something like a design SBOM when you're busy putting together and planning a system, and then prove it showing out by a runtime SBOM, for instance. And this gives us a traceability between a runtime. All these are the deployed things that are on that runtime. Hey, and this build image was used and deployed. And oh, it was built from these other built images. So that's a traceability that the security people are looking at right now. And if we actually look at safety critical systems, we need to take it probably down to the source level. And the nice benefit of doing that is you get rid of a lot of false positives. However, so when you have a security fix coming in, an integrator needs to check the safety profile. So you basically get, customer finds something on a deployed SBOM, looks through it, oh, yeah, maybe, goes through the build SBOM, and then go to the source SBOM, yeah, you can say definitively, no, that source is not there, that bug is not there, or oh, yes, I've got a problem, okay, I'm going to talk to my integrator who gave me that component, who then has to go in and fix it and create a new build SBOM, check the safety profile, pass it on back to the customer who then looks at getting it deployed, and a new deployed SBOM comes in that references that build SBOM. This type of modularity and flow will enable us to scale. And if we're talking about using the SPDX relationships, we can start to link this evidence that we want to talk about from the safety plans into what packages are there, how they're generating, what the test framework is, what the final executable is, and then the evidence and logs, and relate that back into the safety concept. So using metadata about the software, we can basically look at trying to get this to scale, which means things like, hey, I've got a requirement here. Oh, I've got a bug fix I do have to fix. Okay, fine. Well, I can look back and find from that bug fix on that file which requirement it participates in, or multiple requirements it participates in. And from those, I can know exactly which tests I need to rerun to satisfy my requirements. I've got a new executable generated that goes into the framework, proves out that, hey, I'm hatching the right log files, and hey, that's evidence for my requirement. I'm done. By scaling it, we have a chance of going forward this way. And then, we might need to generate other impact analysis cases. So concluding it up, since I've got that, is work is underway to build the bridge, to bridge these gaps between the functional safety and open source. And I would encourage anyone who's interested in this to, feel free to come up and talk to me afterwards or ask questions. And I don't think I've got time for questions, but if you are interested in learning more about the Charles Bridge, some links here, and there is a museum that's got a lot of information here in the town, so if you've got a bit of time while you're in Prague, I'd encourage you to go check it out. And thank you.